Okay, I think we start out. Some administrative information first. This week we got this room today, but for the rest of the semester we were promised share number 5. It's just upstairs. It's actually a better room, so that's okay. Wednesdays, no room. So we are stuck with R10, except tomorrow. I think I got number 3 in the electronics department, so that's actually a better room as well. But sadly, we have to use R10, I guess, unless I can find another room later on. But share number 5 will be the Tuesday rooms for the rest of the semester, I was promised. So share number 5 on Tuesdays. When it comes to the exercise guidance, we will see how many of you shows up on Friday, late Friday. I mean, it's almost party time then, so we'll see how many shows up. Because F2, it's not that big a room, and it's not so convenient when it comes to having guidance, exercise guidance. So if there is too crowded, I suggest we do the following. We use the cafeteria here. That's open. Nobody's here on Friday anyway, so no problem. Well, they sell beer until 4, so you can have your party starter here. Should be okay. But there, at least in the second floor here, we will have some tables. You can sit there working with the exercises, and I and the assistants can then mingle between you much better than we can in F2. But let's start with F2 this week. We'll see how it goes. We have played around with videos, so hopefully we will provide you with videos of all the lectures. I bought a better camera. That one is rather small, and it's not ours. We had to borrow it and deliver it back and borrow it again, so it's a little messy. But now we have got our own. Just haven't found the on button yet. It's complicated. But we will get good videos. So you will find them on YouTube, links to YouTube, as we go along. You have been given exercise 1. And this is just given as an M file, a Matlab file. That exercise I want each and every one of you to hand in individually, not working groups. I want every one of you to show me that you can handle Matlab. So if you are a little weak on Matlab, put in some effort on exercise 1. And show up on Friday, you will get help. I put out some material under here. Learn Matlab in 1 hour, or also Appendix A, Introduction to Matlab. It's very short. If you are sort of blank in Matlab, you can have a peek into those. But remember, you will be given scripts by me, and then you just modify it. So it's not a programming course. We use the Matlab as a tool. So it shouldn't be that hard, I think. Okay. Any administrative questions from you while we were at it? No? That's okay. Good? Good. Last time we went through Burton's chapter 1, so now I will start on chapter 2. Before I do that, I want to show you an example, play around with Matlab, and sort of that will also be some hints for the exercise number 1. Let's see. It's just very small indeed, wasn't it? Can you read it? Well, you'll find the Matlab file Alternative Learning, exercise 1. So it's two different problems. Problem 1, you sort of have to solve from scratch, but I'll give you some example how to do this today. How to solve such an ordinary differential equation using Matlab's built-in routines, TEP4240 and so on. Second problem, that is playing further around with this rabbit foxes problem, and also introducing hunters as well. So here the first part of the script is actually given to you, more or less. Okay, so that was exercise 1. Then we start into Matlab and system simulation by looking into an example. We haven't learned much yet, but much better to look at an example than reading all this boring theory. So we have what's called an actuator. A device that may make it possible to position a mass at the desired location. So we have the following problem. Here we have a pool of water, and then we add a pump like this, a long pipe, and then all of a sudden we expand the pipe, and inside this big pipe here we put a piston, as we call it, a plate that can move back and forth, coupled to a solid rod, and here we hook up our mass. So here we have mass M. On the other side of the mass we will have a spring attached to a solid wall. So here, this pump. This pump can, well, a pump can do two things in fluid mechanics. He can give pressure and he can give a flow, or a combination of those. But here we call this pump is a pressure pump. So he sort of specifies the pressure here. P force as a function of time. So he is given, we know him, we can control him. That's our input function into this system. So he's well known. For the pipe flow here, we have resistance. And RF for friction. Inside this huge cylinder, we will of course have a pressure, and we will have an area here, area A. Now this mass, he will slide back and forth on a liquid film, sort of a oil that is lubricated, lubricating a plate or something. But a resistance force here, resistance force, what should we call him? FB. And the model, very simple model for a resistance force, sliding resistance, will be the force is proportional to the velocity, but operates always in the negative velocity direction. So V, the velocity for the mass, negative, the force acts the other way. And then multiplied with a constant parameter B, something like that. The spring, has a stiffness K. And before we begin to model and simulate this problem, we have to decide what is the positive direction. And here I choose positive direction to the west. So X. So our task here, model and simulate this system. In other words, find the position of the mass for all times given an input function for the pressure. So find x of t for the mass. Model the problem. Well, we have done a lot of modeling already. Here is a resistance force. That's a model. The pump system here, sucking of water from a reservoir, so we know him. Well, that's of course a simplification for a real problem, but okay, there exist pumps that provide you with a power. That's okay. Next, can the pump go the other way? Well, of course it can. So you can spit out water into the reservoir or push the water into the system. You can work both ways, that's quite okay. We need a spring model as well. And here, big question, resistance force from a liquid stream, moving liquid flow. So how do we start with that one? Fluid, pipe flow, resistance. And then it's a question, as you all should know, is it laminar, is it turbulent? That's quite a different answer to the question, how big is the resistance? We assume laminar, make it simple. Laminar flow. Then from basic fluid mechanics, you should have learned the following. The pressure drop in a pipe flow, given that he is providing a certain volume flow Q, they are proportional. So the pressure drop proportional to the velocity in the liquid in the pipe. If it's turbulent, then typically this will be to the power 2 or 1.7 or 1.8 or something like that. And you have a turbulence model into it. Here, lambda. Here we multiply now with a parameter, and it reads 8 times the length of the pipe, viscosity, pi, radius to the power of 4. And of course, this is just parameters, so here we call it an RF, which then is a constant. So pressure drop due to friction is proportional to the volume flow. That is actually equation number 214 in chapter 2. So we will address general resistance there. Okay, that was the pressure drop. So if the flow is moving to the right here, we know PS as an input. Then we know the pressure inside this piston here, the big cylinder. And then we can get a force acting on this area, the pressure times area, and we know the force acting on the mass. So now we are getting somewhere. We need the spring force. Spring force, Fk. also a very simple model, a linear spring. The force will be proportional to the displacement. So here now we should have x minus x0, something like that. X being the position of, or actually a delta x, the position of the spring, while x0, that's the neutral position for the spring. X equals x0, then the spring doesn't give any force either way. That was spring. And we have the resistance force from the sliding mass here. Here it might be a question from some of you. If you have learned basic mechanics, you have a mass sliding on something. What's the resistance? What is the resistance? It stops. It's the resistance. But it's not proportional to the velocity, is it? How do we model that one? Solid mechanics, you remember? Then, well, of course acts in a negative direction, but it's not proportional to the velocity. It's proportional to the normal force from the floor to the mass. That is dry friction, we call it, Coulomb friction. But here we have modeled it somewhat differently. So how is that possible? Or is it realistic at all? Well, as I said, imagine a small oil film here. Okay? And you should remember from basic fluid mechanics, moving wall, solid wall standing still, and you have oil in the center. What's the velocity profile? It's going to look something like this. Then you're talking a correct flow. What's the force you need to use to drag this plate here? Well, this force must goes like viscosity times the derivative of the velocity with respect to y, u and y, which then equals mu times some velocity v0 or whatever you call it divided by h. In other words, force is proportional to the velocity. So there you have it. The force, resistance force, proportional to the velocity. Okay? Good? Did we miss anything else then? No? Okay. Model. We have a lot of elements now. Combine them to find how this mass is moving. So we need dynamics. Newton 2 for the mass. Of course, that is the finishing argument here. That is the important equation. So how do we write this one? Mass times acceleration for the mass, x with double dot. And then what will we have? The sum of the forces on the other side. Well, we have a spring force, definitely. We will have a pressure force here. If you have a pressure here, the force will be Fp equals pressure times area. But I have the positive direction to the left, so that must be minus Fp. How about the spring force? Say if x is bigger than the neutral position, x0, that means we have moved the mass to the left in the positive direction, then I get a negative force acting to the right. Yeah, that makes sense. So V must be positive. V is negative, and we have the resistance force So that should be negative, shouldn't it? Minus LP, let's see. If she is moving to the left, she's moving with the positive direction, then the velocity is positive. Then he should act in the negative direction. Well, then we have the minus there already. And then finally we need, what else do we need? Nothing more. I'm missing the resistance here. The delta P pressure drop in this pipe, but you will enter here. Let's do that. He will be the source minus this delta P. So let's see if this one is correct. X minus X0 spring force, and then we have the pressure. Well, that should be delta P, which then again was Q times this one. Let's see. Q times R F, like that one. Well, no, we can't use Q, sorry. F multiplied with, and what is Q? Volume flow. Well, that will be the velocity, V. Velocity for the mass will be the same velocity as this piston here, times the area. So that's the volume flow. And well, we can call him V, that's okay, and area A. Less pressure minus delta pressure operates on the area A once more to get a force. And then finally the last one. Minus the velocity. Something like that. Only one mistake there, I think. If he is moving, the mass is moving to the right. It's moving to the right in a negative direction. Then the pressure here, P, will be smaller than this one. I mean, you have a bigger pressure here, and then it flows to the right now. So then, due to the resistance, the pressure here is going to be smaller. So we have to subtract something here. And yes, we have a minus here, subtract, this is the delta P. But V is negative already. It has to be positive. Else I think it's okay. Any objections to that one? Everybody agrees? Okay. Doesn't look too good at first glance. X is the unknown function. Double derivative. And he appears here as an X. And then we have another function V. Doesn't look too good, does it? So how do we do this one? As I showed you last time, when you have a second, third, fourth, 17th order ordinary differential equation, rewrite it as a set of first order. And do not accept second order derivatives. Get rid of it. So we have to rewrite our system. How do we do that? Well,
excuse me.
Yep.
Can you please explain again why the sign has changed?
This one?
Yeah.
The reason is my stupid choice for positive direction to the left. So when you now try setting him to be positive to the left or negative to the right, then you can see, okay, should this delta P be positive or negative? So that's how you have to decide this sign for yourself. Here you have to think. I know it's annoying, but you have to think. Much better when we start with this bone graph idea, then you don't have to think. It's automatic. I'll show you later. But here you have to sort of find out for yourself what is the proper sign when it is to the left to the right. You just have to go through everything, need to be sure. Also, you will typically see it when you start programming and playing around with different parameters, different numbers. Then, if you have done something wrong here, it should be possible to arrest or find your bug in your code. So that's a way to find say any mistakes you might have done. Let's do it another way. Other questions? No, that's okay. Okay. Rewrite this equation here as a set of first order. Well, here we can do it a little bit physically. This mass times acceleration you can write as mass times velocity derivative. That's the same. So we can use velocity as one parameter, one unknown. Then I'll write this equation here on the form v dot equal. Just divide by m, and then what we get, we'll have minus k x minus x0 divided by m minus vs plus rf times v times a multiplied with a divided by m, and finally v velocity divided by m. And then we have one more equation, say x dot equals v. There you have it. You need the last one. Remember, you still have an x in your expression. If we had skipped this term, just forget the spring. Then you see it's a first order equation with the velocity alone. Then it's just a single equation, a first order system. Now we have a second order system. And now we are ready to do the programming, actually. Well, not entirely true. We need something else as well. We need initial conditions. So we do it easy. Zero velocity when we have the position x equals x0. What does that mean? X equals x0. We don't have any spring force. I will not have a velocity. Then this one is gone, and this one is gone, and I am left with the pressure. Then gives rise to my acceleration directly. Well, that makes sense. Should be okay. If you want this to be a steady state situation, then this guy has to be 0 as well. Then nothing is going to move. To make it easy, we choose x0 to be 0. We don't need it. It's just an offset anyway. So now it should be possible to create a script. And doc. It's a little small font, isn't it? Can you read this? It's okay? Okay. So with any Matlab script you start with, always start with those 3 lines. Clear all. He really freshens up the memory, removes any old mistakes you might have done. Close all, destroys all old figures, and CLC. He clears up this command window you have here, where you will have a lot of error messages, but doing a CLC removes it, and then you know any error messages there is going to be from the last run. So that's CLC, always a very good idea. Then we are going to need some parameters, some constants into our problem. Always start with the constants. So what do we have here? We have a resistance, RF, equal. In this course, this is now going to be a typical problem. You have something you want to simulate, but you have no idea what the numbers should be for all these parameters, all these constants. What should the resistance be? I have no idea. When you have no idea, put everything to 1. That's the first guess. Put all the parameters to 1. Then you know from the dynamic problem the time scale, the interesting physics is going to take place with a time scale of 1. Then you have an idea what the time unit should be. So choose everything to be 1 first, and then you can always play around with numbers later on. So our F is 1. We need the mass. It can then be 1. We have a parameter here, B, should be 1. Area should be 1. That's a big area, 1 square meter, but okay. Do we need more? X0 was 0, so forget him. I think that's all our constant, isn't it? Okay. On the K, yeah, the spring stiffness, thank you. We need that one as well. K is 1. Initial conditions, velocity is 0 and the position is 0, like that. And now I want to solve this using first order Euler step. So for this derivatives here, you put in first order Euler step, meaning we need time, maximum time, set him to be 10. I said the time unit should be 1, but 10, then I'm dead certain I should cover most of the physics. And then is the question, delta t, what the hell should he be? I have no idea. We have to try. Point 1. Maybe that's a little bit too big, but let's try. Let's try and see what happens. So now we can start making some simulations here. I need a figure 1, like that, and then I say hold on. It's just to tell any graphics that follows should go into the same figure, and then we start for time equals 0, step time delta t all the way up to maximum time. And then we have our equations. What should we write? We could write it like this, V dot equals. And then we have the right hand side directly as it is. Minus k multiplied with x. And then it was minus, parenthesis, a ps. I haven't ps yet. That's something we need. Plus rf times v times area. and then multiplied with area once more, minus b times velocity divided by m. I am missing some m here, aren't I? Yeah. Divided by m, divided by m. That should be correct. And then before we do this, PS has to be something. Let's start with 0. PS is 0. Then, as I said here, nothing is going to happen. Nothing should happen. If you don't have any driving force, you start in a neutral position, nothing should happen. So let's just check that that one is okay. V dot, and then we have x dot equals v. That's it. And now for the first order Euler scheme. We update v equals the old one plus delta t times the derivative. Same with x times x dot. And then we plot time x time v. Should be okay. The x, well, he can be the red circles, and the velocity, he can be blue circles. Let's see if that one works. Is it correct? Have I done any mistakes? Yeah.
Can you tell me why you list the x0?
Sorry, the what?
The x0 in a v dot equation.
Yeah, I skipped the x0 just for simplicity. I choose him to be 0.
Yeah, but you said before that x might be x0, so why where's an x?
Well, if you wanted, you could have addressed x0 here. I mean, it would be sort of the same, yes. X minus x0. We could do it like that, and then define x0 to be 1,017,25, whatever you want. It doesn't matter. So I just chose him to be 0, that's all. Just to make it simple. But if you want, you can keep him. That's fine. Your call. So x0 is 0. It's okay? Let's try. See what happens. Untitled. Yes, that's an okay name. And absolutely nothing happened. Sounds good? Then we change PS to be something different than 0. So now what should happen, everything is at rest, time equals 0, then all of a sudden we switch on a pressure here. So he should then push our mass into this spring. So now it's a question, how strong is the spring, what about all the resistance here, how fast will this go, and will this mass move back and forth, or what will happen? Let's see. Yeah. As you can see, things will happen on a time scale roughly around 1. Here I chose a time scale of 10. Then you are quite certain you will cover most of the physics. Why did he become gray? Are you breathing too hard on this side of the room? Strange. Okay. If we want to have a more, say, more interesting solution, we can now start playing around with the numbers. I think I have a nice setup here. The spring stiffness. Spring is normally quite stiff, quite hard. So 100. Then what's going to happen? he blows up. Then my delta T is obviously too big here. So now we have a much faster dynamics into our problems. But we can sort of smooth him down a little bit. We take a bigger mass, 10 kilos. Yeah, that helps a little bit. Still, we shouldn't get so complicated solutions and something like that. I'm not sure if I believe it. Remember, is this a linear equation system or is it non-linear? Anybody dare to give me an answer?
Linear.
It's linear. It's a linear equation. Linear equations, they normally behave smooth and nice. I'm not sure I believe that. Let's put up some more resistance here. Rf can then be, say, 10. Good. If you look at the scale, 0.03, 0.04 to the on the y-axis, we put everything down here. So now it's a question: should we believe this one or what? One way we can test: use a smaller delta T, and then see, will this change the solution or what? Oh yes, it did. A lot. So finding a proper delta T will, for us, involve a little bit of trial and error. So this one, yeah, we can believe him. It's not much displacement, but if you put meters and seconds and units for all our parameters, he's moving 2.5 centimeters back and forth here. Okay. Any questions so far? That was okay. We will then continue next lecture by looking at Matlab's built-in TEP4240 or UDE solvers. Much more accurate, easy to use, but it's a little black box. So let us take a break.